minus means to calculate my work. When pressure changes, constant pressure, pressure is constant. That means pressure is still the same thing. This one though is not changing P, so it does not affect him. But the idea is always like for something to be affected, it has to be changing that stuff. So like in this one, it was changing T being 0. So 0 times whatever will give you 0. For this one, just bringing in P here. The P, there is a pressure, it's just that there is no change. So that pressure has a value. Or if you should say change in pressure, that is when it is down 0. I don't even understand. So temperature, just like in this case, temperature 1 is a value. Temperature 2 is a value. But then change in temperature is 0. I don't even understand. That's what same means. I'm not hearing. Yeah. Yes, that's in gas laws. Call it out. Continue. When I say something is dependent on something, what I mean is that it had a value, you changed, and because you changed, me, I also changed. So for those kind of formulas, to always talk of dependence, most times it's either a formula that we are doing showing direct relationships, that's relationships, or number 2 is going to be a formula that has changing. So like in this case, if I have something like this, internal change in internal energy is NCV change in T. Classically, I know of course if this value is changing, whatever value you have here should also change, right? But the thing is that the way I'm writing it, when I'm dealing with a system, I assume that that system does not change in, like it is a closed system, so there should be no loss of matter. So it will not, this thing will not be affected. In the same similitude, when I'm talking about internal energy, we assume that volume is constant. Like if volume should change, according to this formula, it has no effect on internal energy. But if temperature should change, so my own is that the change in V is due to change in T. That's the person it affects. Don't worry, leave this other formula. It's more of gas laws and it's just used to derive U. But you hardly use it now. Have you had any calculation that you have used this formula? Which one was that? What did you say? Okay, yeah, those have different formulas now. You have been taught it has been used. Okay, the Lord will bless you in the ideal gas in Jesus' name. Amen. So please, let's come back here. Don't worry, I don't want to stop ideal gas today. Now, a gas in a cylinder has a pressure. Gas in a cylinder has a pressure of 2 times 10 raised to the power 5 Pascal. Gas in a cylinder has a pressure of 2 times 10 raised to the power 5 Pascal. Gas in a cylinder has a pressure of 2 times 10 raised to the power 5 watts Pascal. As shown in the figure below. The piston has an area of 3 times 10 raised to the power minus 3 meters square. Piston is spelled Piston. The piston has an area 3 times 10 raised to the power minus 3. 3 times 10 raised to the power minus 3 meters square. And is pulled slowly a distance of 10 millimeter. And is pulled slowly a distance of 10 millimeter. If the cylinder was insulated, if the cylinder was insulated, calculate the change in internal energy in joules. If the cylinder was insulated, calculate the I'm listening. Yes. What does it mean? Does not allow heat to pass. So please, the idea of insulation just means that heat does not enter. If something is insulated, it means it cannot enter it and it cannot leave it. So which kind of process will we be dealing with? Adiabatic process. Alright, so let's come back. Please, what was given in the question number 1? Yeah, let me draw the piston. Alright, let's start. What was given number 1? Pressure as what? Number 2, area as what? Minus 3. What else was given? Distance. What was distance? What was distance? 10 millimeter. If you change millimeter, this will become 0. What? Let's divide by 1000 now. 1 over 100, 0.01 meter. Alright, please. Now the question is that we should find what? Internal energy. If we are dealing with which kind of process? I hope we know why we are saying this is an adiabatic process. Because it is what? Insulated. So that means change in U is what? Change in Q is what? 0. Alright, please look up. The formula is that change in Q equals to change in U plus or minus W. When did I tell you that to use plus? Work done by the system. When are you to use minus? Work done on the system. When you look at this particular system, looking at that picture, they said it is pulled out. Listen, a piston that has a particular area is pulled out. If I pull out a piston, think of a syringe. You've seen a syringe before now. So that's the same pattern. If you drag it out, are you increasing the volume of that containing syringe or decreasing it? Are you raising it up or dropping it down? Yeah, that's the idea. When you bring out the syringe, you are raising it up. When you push back inside, you are doing what? Decreasing. Or another idea is that anytime they say something is pushing out, pulling out, that tells you that the system is working on the surrounding. But if it was being pulled in, that tells you that the system is working, the surrounding is working what? On the system. So please, will this be positive or negative? If I'm working, if it is expansion, will it be positive or negative? Alright, so we deal with positive. Now we continue. This one is what? 0, right? So we now come to change in U. Change in U is what we are looking for. Plus, what is your work done? Pressure times volume now. So what is your pressure? What's pressure, please? Sorry, please. I can make this solve formula. Change in U will be what? Minus E change in V. So this will be minus 2 times 10 raised to the power 5 times. What is the volume? Okay, yeah, we have to look for volume. Volume is area times change in distance. So what is the volume? 3 times 10 raised to the power minus 3 times 0.01. That will be 3 times 10 raised to the power what? Minus 5. If I have minus 5, I have plus 5, they will cancel now. So my final answer will be what? Minus 6 joules. That's your answer. Any question? Yes, ask. Yes. She's asking a question, must I know what type of process? Most questions might not even have defined it by process. But if for any reason in a question, I tell you something that should give you the process, you must take note of it. And that's why you read a question. Like, there are classical questions where you'll be given everything that will be, you will be given this one, to find another person. But there's those questions which are a bit tricky, where I'll not tell you anything. Okay, imagine in that kind of question now. If someone reading the question does not know that insulation means adiabatic process, that person will fail that question because he will be looking for, when you write out this formula, there will be two unknowns. Then if you understand. So the person will now look for other formulas to solve what is not possible. Are we together? So please, what we have to take note of here is that for this particular scenario, insulation was mentioned. Or sometimes they can just clearly tell you that heat does not enter or leave the system. Telling it is adiabatic. They can tell you that it's a process that is constant temperature. Are we together? So that tells us that which kind of process are we dealing with? Isothermal. They can tell you that there is no change in volume. Which kind of process are they telling you about? But there are questions where there are no parameters, none of those criteria are mentioned. So that is just generic. Everything stands. Are we good? All right, so we continue. Is there any question concerning this? I hope you could talk. There's a lot. No, classically in physics, most times we use positive. And like someone that carries positive around will not fail in physics. Like most times it's work done by the system. But just so that you have accurate knowledge, I'm saying that the reason why this was used as positive was because in the question it was clearly told that the piston is pulled out. And when it is pulled out, think of a container. I have a lid. I'm pushing it out. That means the volume of that container is doing what? Increasing. And whenever the volume of the container increases, that is termed what? Expansion. And we have learned, me and you, that expansion is work done by the system. That whenever the system is doing work on surrounding, it's pushing out. And that will always give me my work done as what? Positive. But on the other hand, if for any reason they told you that what was moving was pushing in, they should be clear in their communication. Like if there is a thing in a question, I have to be very clear. Like the test of knowledge is not that I make something vague. The test of knowledge is that I made it clear, but this person does not just know. That's why I did not know how to answer. So if I'm bringing out the question, I want it to show work done on a system. I'll either clearly say in the question that this system, there was work done on the system was given as this. Now expecting that you know that whenever work is done on, I should have used what? Minus. I don't know if you understand. Or clearly, I'll now tell in that question, it is pushed in. Or sometimes they might not even use those vague terms. They don't even understand. So if they want to bring in work done on, they will be very clear. They don't even understand. But most times in physics, what do we always use? Work done by, which will always be what? Positive. Let me give you a simple question here. My brother said, please, I don't think I will need you to write. Just listen. First thermodynamics is written as a particular first law of thermodynamics is written as this. The first law of thermodynamics can be written as, listen now. The first law of thermodynamics can be written as this for a particular ideal gas. Like this is not generic. We know the normal formula, please. So this is just for someone. I don't know if you understand me. Are we together? So this is just me writing for someone in this question. They said which of the following is most correct. So this is what we are going to do. From what we have learned, I want us to scrutinize each of the options. Option A, change in U is always zero when no heat enters or leaves a system. Is that correct? Change in U is always zero when no heat leaves or enters a system. Is that correct? What should be the correct thing? Change in Q. Whenever heat leaves or enter, who is the parameter that defines heat? Q, not U. So that makes that option wrong. Option B says that in this particular place, the change in W here is work done by the gas. Is that correct? For us to know if this is correct, we have to arrange this in the normal way it should be. What should be the normal way? Who should always be the formula? So let's make it formula with the subject. If I do change in Q to now be what? So you now observe that in this particular parameter, please, in this particular formula that was given in your Nelson and Parker, what was this work done? Was it work done on or by? On the system. So that makes that option B wrong. I don't know if you understand. So they say here that in this particular, in the written law, work done, the change in W is work done by. That's wrong. Option, the next one here says that change in U is 0 when heat is supplied and temperature stays constant. Is that correct? Change in U is 0 when heat is supplied but temperature stays constant. Is correct now. Anytime temperature is constant, that means change in temperature is 0. That also means change in U is what? 0. Which particular process are we dealing with? Isothermal. So that is the correct option. The other option they gave you is that change in Q equals to minus W when temperature increases very slowly. What does that even mean? If temperature should increase very slowly, as far as there's a change in temperature, I cannot get rid of my U. Are we together? I only get rid of U. Change in U is only 0 when temperature is constant. So as far as temperature has changed, this formula cannot hold. Don't even understand. So this their formula will hold if I was dealing with an isothermal process. That means temperature is constant. So if temperature was constant in this same formula, what will happen? Change in U will also be constant and you cancel out. I don't even understand. So the formula would have been correct. But that would have been if temperature is constant. So that is wrong. The last one is that the law is due to property of gases. I don't know what that means. So we go forward. Now we have another question here. This one is just a simple mathematics test of knowledge now. When two blocks, I don't think you should write. Number 3 is still on your Nelson. When two metal blocks, X and Y, or iron and steel, so there's X, there's Y, having different masses, are in thermal equilibrium with each other. Please listen. When two different metals, X and Y, X is iron, Y is steel, they have different masses, but then they are in thermal equilibrium with each other. Which of the following is correct? So they gave different options and tell you to mention A, B, one of these. Let me just list the options. Option A, or number 1, each has the same amount of internal energy. Is that correct? If objects have different masses, do they have the same amount of internal energy? As far as there is difference in masses, what is mass? Mass is the quantity of matter, and quantity of matter will affect number of moles, and it will affect internal energy. So please listen. Quantity of matter too. You know that when the molecules are plenty, the movements, all those kind of things. So you have to remember what was internal energy? The sum of all the kinetic and potential energy. So please let's read that option again. The option says each, that's X and Y, who have different masses, have the same amount of internal energy. That is not correct. It shouldn't be correct. I hope we are together. Because there's different in masses, they are not the same quantity of matter. So they can't have the same internal energy. Number 2 is that their temperature are the same. Is that correct? Why is the temperature the same? Thermal equilibrium. Which rule is that obeying? Zeroth law. All right. Now we go to the last one. That there is no transfer of heat between them. Now the word they say here is no transfer of energy between them. Let me use heat. There's no transfer of heat between them. That would be correct now. Heat should not be transferred between them. Why? Because they are in thermal equilibrium. So there is no net. I think that would have been the better word. There should be no net transfer of heat between them. So that is that. But so the best option here, they now say 1, 2, 3 is correct. Wrong. Only 1 and 2. Wrong. 2, 3. Correct. D. Only 1. Only 2. Only God. So we go forward. This other one is also a simple question that we can think out. They said a container has 1/2 filled with an ideal gas X. Separated by a plate P from the other half, which contains a vacuum. So this is what they're saying. Okay, I have this container. This big container is divided into 2 halves. One is called X. One is called Y. Listen. One big container divided into 2. one has gas. Like there's something that separates it. What separates is a metal plate, P. Are we together? So let me check. Okay, there was a diagram, they drew it. So I have something like this. X and Y. X is where you have gas. Y is where you have your vacuum. Is that okay with everybody? Into two equal halves. Now they now said, when P is removed, that's when you take out the plate. P was what separated them. When P is removed, X moves into Y. Oh, these people, they use English bonus. So look at the object. The object was this way. And remember, it was divided into two equal halves. That means this is Y. Then I say when P was removed, the X moved into Y. Let me look at they use the word. Yeah, it moves into Y. You know how a gas works, and even know how gas works normal. When you fill gas, even if you fill 1 kg inside a 4 kg cylinder, it will spread now. As far as there is space, it will spread. So now it's just that when there is this plate now separating it, the volume of the gas will be restricted to here. But when this goes out, the volume of gas will do what? Spread across. So that means if we say that these people are the same, let's assume, look at the phase gas. What are they trying to capture? This phase side, it had a volume, right? So if this volume of X and volume of Y is the same thing, and I take out this thing and the volume has flowed into the two, what does the new condition mean? Look up, please. In the first scenario, I had volume that was just V. In the second scenario, there's no separation again. That means the volume has flowed everywhere. What will be the volume now? 2V. I don't know if you understand. So now the question was, now which of the following statement is true? First statement is that X decreases in temperature. X decreases in temperature. X decreases in temperature. Whenever we mention decrease in temperature, what do we mean? When we mean temperature, what are we talking about? So that means what has happened? If we were to define that, what does it? Let me do it like this so that I'll make it easy for you. Let me go down to some other options. They said there is no, in option C says no work is done by X. Is that true? No work is done by X. Is that true? Is there work done by X? Yes. Because there is change in volume, work is done. So he has flowed out. So work is done by the system. So that's, there is actually work done. Number two, they say that X doubles in pressure. Is that true? Let's go back to our normal knowledge. In Boyle's law, what's the relationship between pressure and volume? Inversely. So if volume has doubled, what should happen to pressure? Pressure should be what? You should decrease by half. I hope we are together. So that makes that option wrong. So pressure X does not double. The next thing is that they I don't even understand. So let me define them one after the other. Let me give you yes. You can use Charles' law too. Yeah, I think Charles' law can help it too. You guys using Charles' law? Charles' law is early. Is it direct? It's direct. So Charles' law does not explain it. But if I'm using Charles' law, as volume is increasing. So Charles' law does not extend it, please. Now, please, we come back here. So over here, please, look at what I'm saying. That if, listen, please, I'm assuming that in this particular scenario, to move from here to here, that there is no heat being introduced, because nothing was mentioned about introduction of heat to this system. All they said was that P was removed. And because P was removed, which was like a resistance or a partition, the gas flowed into the other side. So that means volume had increased. So whenever volume increases and it is increased, that's work done by the system. I hope we are together. I hope we are together. You now look at the formula. 0 equals to change in U plus W. So that's change in U is what? Minus W. So please take note. This means that anytime I'm doing work by this system, who is suffering? Internal energy. So whenever you are doing work, internal energy is doing what? Falling, decreasing. So when you look at the options, option A, if internal energy decreases, that means temperature is also doing what? Decreasing. So that makes option A correct. Option B, internal energy can never go up in this situation. Option C. What's option C? Oh, you don't know. Option C talks about work done. He said there is no work done. We know from what we have learned that there is actually work done. Option D talks about that there will be doubling in pressure. But we have established that if we use normal Boyle's law, pressure cannot double. But aside from that, when we look at these formulas, we don't really see an effect on pressure. Our concern is always volume and temperature. Then now, beyond that, we now go to the container expands. We say what expands? The gas. Next question, write this one. A gas has a volume 0.02 meter cube. A gas has a volume 0.02 meter cube. A gas has a volume 0.02 meter cube. At a pressure 2 times 10 raised to the power 5 Pascal. So volume, pressure, and a temperature of 27 degrees Celsius. Yeah, I'm too fast. Let me ask you something. I hope you know that when you're dealing with temperature, ideally in physics, temperature you use, what's the sign of temperature? So you use absolute temperature. When you're dealing with gas laws, you use absolute temperature. When you're dealing with this too, use absolute temperature. Don't make use of temperature in degrees Celsius. Because temperature in degrees Celsius, the only time you should even use temperature in degrees Celsius is if, listen carefully, if you are using change in. So when you are doing heat, for example, when you were taught heat, during it, they will tell you change in T, you can subtract it. Because even though you change it to Kelvin, when you still subtract, it will still be the same value. I don't know if you understand. So the correct definition of Charles' law will state that volume is directly proportional to absolute temperature, not just temperature. I hope we are together. All right. So please, let's come back. A gas has a volume of 0.02 meter cube, pressure of 2 times 10 raised to the power 5 Pascal, and temperature of what? 27 degrees Celsius, full stop. It is heated at constant pressure. And you see that thing I told you? They will not say it without being very clear. What is it heated at? Constant pressure. So what is that? Isobaric. So it is heated at constant pressure until its volume increases to what? 0.03. Heated at constant pressure until its volume increases to 0.03. Heated at constant pressure until the volume increases to 0.03. Question says calculate the external work done. External work done, that is work done outside. That's work done by the system. But if it is not defined, listen, if nothing is defined clearly, always take it as work done by in physics, please. Now we continue. Calculate the external work done. That's number 1, right? Number 2, the new temperature of the gas. That's the second thing to calculate. New temperature of the gas. Number 3, the increase in internal energy. Increase in internal energy of the gas. If mass is 16 grams and molar heat capacity at constant volume, if mass is 16 grams and molar heat capacity at constant volume, can you write CV now? Is 0.8 joules per mole per Kelvin. I'll repeat myself. From what do you want me to repeat? Calculate external work done, new temperature of the gas. Like those are 2 different things. Then the third thing is calculate internal energy, increase in internal energy. If the mass is what? Mass is what? The molar heat capacity at constant volume is 0.8 joules per mole per Kelvin. They tell you what? Time. You don't need the type of gas now. And its molar mass is 32 grams. So who is this self? Who is this person they're talking about? Oxygen now. But no need to stress yourself with all those things. It's chemistry that we want to do all those things. Can I go on, please? Now let's solve that question. What have been given in that question? Is there anybody that can read loud? What has been given? Read. Go. So there is pressure at a particular point, which is what? There is volume at 0.02 meter cube Pascal. Are we saying? At that same time, temperature is what? 27 degrees Celsius. Like I said, you change to Kelvin. What will be the value? I hope we are together. Number 2. So there is something. What did they mention? What is that word they mentioned? Constant pressure. What does constant pressure tell you? That when I move from P1 to P2, it was still the same. So that means change in P is what? 0. But of course, it's not very significant to calculation. Continue. B2 is what? Meters cube. I hope everybody in this class is following us. What's the question? Is there anybody that cannot solve work done? What will be work done? P change in V. What is the P? What's the volume? Bigger the V2 minus V1. 0.03 minus 0.02. What's your answer? 2 times 10 raised to the power 5 times 0.01. When you calculate, I hope we are good. That's 2 times 10 raised to the power 3. That's number 1. What was number 2? New temperature. Anytime they give you things at one place, they now give you things at the other place and ask you for new. What is the idea? Gas loss now. So you don't even stress yourself. Me, I don't always like stressing myself to think of which of them. Do I know them individually? But I like using P in general gas equation, PV, like so that I will not stress myself. But of course, you can use anyone you want to use. Classically, the one to use here will be a constant pressure. That will be Charles' law, which will be so. But what I do is I write the general one, no matter the one you ask me. And how will I now start it? And now observe that P1 is the same thing as P2. So what does that mean? Are we together? So that changes my formula to V1 T1 equals to V2 by T2, which is actually what? Charles' law. Now let's go on. Now please, we know V1, we know T1, we know V2, we are looking for T2. So very simple. What's V1? What's temperature 1? What's V2? What's temperature 2? Unknown. So you cross multiply. I believe we are following me. You are not answering me again, no? Are we together? So T2 is now 300 times 0.03 divided by 0.02. When you cancel, your final answer should be 450 Kelvin. Like, this should cancel and give you 3 over 2. 3 over 2 is 1.5. 1.5 times 300 is 450. So that's how you get 450 Kelvin. Lastly, what was the last question? Internal energy. Internal energy. How do you find? They ask for what? Increase in internal energy. How do you find increase in internal energy? Change in U is what? NCV change in T. Do I know my change? Do I know my temperatures? I know initial final. Do I know my CV? Do I know my number of moles? How do you find number of moles? And please note, for number of moles, you don't have to change it to kilogram. You know, chemistry, we don't do kilograms. Like we use more of grams because they are usually in very minute quantities. So if you change to kilogram, it will be so we having 0.0000 the value. So chemistry, we use more of grams. It doesn't make gram the SI units. In physics, when we are calculating for standard formulas, especially in mechanics, you use kilogram. But for here, whenever you have to deal with something that has to do with number of moles, or you have to deal with something that has to do with gas loss to some extent, where you can use it, please, you can use it in grams. Observe here, We said that number of moles is what? Mass over molar mass. What was the mass? 16. What was the molar mass? When you divide, what is that? 0.5 moles. So when you bring it to this formula, 0.5, what was your CV? 0.8. What is your change in this? 450 minus 300. That is 150, right? Is that okay? You say now 50. So 0.5 times 0.8 times 150 is what? 60 what? Joules. So this is your final answer. What if in this same question, I'm adding this one. They ask you what is the heat, change in heat in this system. What will be your answer? It is well done by, so that will be change in Q is change in U plus W. So that will be 2000 plus 60. What will be your answer? 2060. All right. That's when Jesus will come. All right, so that is that for that. Let me go to the second thing. So I'll do second law and then do efficiencies. We'll do third law and we're done. So for second law, what's the second law? Statement of second law. Where did I stop with the questions? Any question with this, please, this calculation? Our online people, you can be asking them if they have questions. I don't know if they're even there. I will trust the Lord for them. Any question on this question? Any question on any of the things you have done so far? Man of God at the far end. Any question? Charles law only works at constant pressure. So why that thing is probably not correct is that we are not so sure the pressure was constant. You understand? All right, so please, can we continue? Just like that wild assumption I did about pressure and volume, in that one I was trying to show with Boyle's law. We are not so sure entirely because, truthfully, we have to be absolute that there is no change in temperature to be sure. But in this case, we can think of it if we have accepted that it's adiabatic, no heat is introduced, so we can believe. But let's just leave it, please. Now, please let's come back here. And the question is always which of them is the most correct option. We come back here, please. Can I continue? Can I continue? Yes, thank you, ma. What does constant? I've been saying also you do change in P. Yes, I can still use pressure 1, V1, T1. But when I come to P2, I have to use the same pressure, which would just mean that it is constant. All right, please, let's come back here. Now, yes, I want to hear statement of second law. Ma, did you talk? Have you talked in this class? So now you're the person behind. Second law. Thermodynamics. Electricity is which form of energy? Electrical energy. Eh? Yes, ma'am, listening. Anything for me? Second law. There's no wrong answer. You're just saying something. No, you, the person behind you. Let me have a help. Man of God, help. Next. Next person. What were you given in your notes? What was the statement given? Are you with your notes? What was that statement given? Second law given? That's what they gave in your notes. Yeah, please, that's the one I would prefer you use. The efficiency is not 100%. Listen, what's efficiency? Physics students, efficiency, yeah. Work output over work input times 100. Like, what does it mean in English? Okay, let me come to girls. Yeah, woman of God. What does efficiency mean in English? If I say something is efficient, what do I mean? Sorry. Has the ability to function. The next person, efficiency. Said it has the unction to function. Function properly. Okay. I think you are saying it beautifully, but I think summary is just that efficiency tells you about the performance of a machine. How a machine just works. So if I say someone is efficient, higher efficiency means that almost everything I'm giving you, you are doing it at the best possible way. So usually we supply heat to every system. Think of a generator. Most of the machines that we have, the motorcycle, the generator, the refrigerator, heat is supplied to it. And then from that heat now, or whatever it comes in, it is used to do work. But now, the expectation should be that if a machine is efficient, 100% efficient, what that means is that the 100% heat that I supply to that system was used for energy. Then you will understand that when you supply a particular form of energy for something, the system could use it totally for work. But when heat is supplied to a system and some part of that heat is lost, that decreases the efficiency of the machine. I don't know if you understand. So the idea or the concept of second law of thermodynamics just tries to capture that efficiency is not 100%. For a normal machine we have, efficiency is never 100%. That means it is not what you give garbage in that you have completely out. That there is some loss of it. Are we together? So for the sake of what we are doing, classically we have the way machines work. We have this of Otto cycle and Carnot cycle. Which of them is the one we see in refrigerator? Which one do we have in refrigerators? Which one? It's the way the person is saying with so much confidence. Refrigerator has Carnot, reverse Carnot cycle. Refrigerator has reverse Carnot. What Otto will be motorcycles. Motorcycles. So Otto is in motorcycles. Otto is in motorcycles. Yes.
And this formula which equals to mass times gravity and change in height in here. That's and the formula we use to solve internal energy.
No.
Okay, that question they say. So I haven't said anything about metallic and metallic reactions which are going on in the system.
Okay. For the first question, first question, why we cannot use this to solve internal energy? Like we said at the start of the class, internal energy is a function of two energies. Like it is sum of kinetic and potential energy of all. That means I should be able to check. I'll check each of the individual molecules, each of the individual potential energy, add it up together. Check each of the individual kinetic energy and add it up together. So there is no formula that really does it this way. So the formula we use for it. And in that question, we ask for even change in kinetic energy. So change in what? Internal energy. The base formula to use is always that formula we did when it's asked. So please, we don't use it because that one, this formula just defines what? Potential. The other person saying endo, exo. What does endo mean? What does exo mean? Heat is lost. So whenever, if I should have heat coming into a system, what should it show? Should it be positive or negative? When heat is coming into a system, the change in Q, should it be positive or negative? So that means you are introducing something. Whatever is coming in, it's increasing. So whatever the system, the level of it the system had, you have added to it. So that is increase, positive. But whenever we have, that's for endothermic. That's why when we learn enthalpy, it's positive. Please, for that person that asked online, why did not say a lot about it? That talking about endo and exothermic is more of a chemistry phenomenon than a physics phenomenon. So if you're looking through your physics table, nobody will care about those things. So in chemistry, the importance of that will just tell you that the heat there, which will be shown as enthalpy, is going to be positive if it is endothermic, but negative if it is what? Exo. So it says that you are losing heat to the surrounding, but it's not really a classical physics phenomenon, or we are learning. But of course, it's a term that has to do with heat. I hope we can continue. Okay, so yes. Now for my guy, for my loss, yeah, I was saying efficiency. Now I want to do something which will really have to do with calculation so that we can jump. But classically, I've said there are 2 cycles. In your textbook, they showed 2 of them. While I was going to your note, I don't think much was said about them. But I'll just describe them a bit and then flow. Carnot and Otto cycle. I'll draw 2 of them and just describe what they do. So for Carnot cycle, of course, we have pressure against volume. For pressure against volume, we have this pattern. Yeah, okay, I think I saw this somehow in your notes, where they try to show you what the processes should look like on a graph. I think it was shown in your notes now. If I'm doing a graph of pressure against volume, when I say something is isobaric, constant pressure, what do I mean? Pressure against volume, what does that mean? Let me plot something. If this was the way the graph was before, if pressure does not change but volume change, what will happen? You will move this way, right? And it will now be here. So anytime you are dealing with isobaric, this will be the graph. If I'm dealing with isochoric, which is isovolumetric, what will happen? That the same thing will happen. If this was the initial place, what has changed? What does not change? Volume does not change. That means you don't move. You stay the same place. But what changes? Pressure. So this iso what? Iso what? Isochoric. That's isovolumetric. Then also we now have the other one which has to do with adiabatic. All those other ones will be bending. Adiabatic and all those isothermal. Now let's come back here, please. This is how Carnot cycle looks like. I'll just describe the words and then I flow. We start from A, B, C, D. So here we have a particular temperature. Here we have a particular temperature. So Carnot cycle, when you look at that cycle, you observe constantly what we'll be having is that we'll have a cycle of course, you know, whenever you say a cycle, you can begin anywhere and stop anywhere. You know what a cycle means now? You can start anywhere and stop anywhere. So you have adiabatic expansion. You have so please, from A to B, you can note, please note, A to B. From A to B, they at constant temperature. That means A to B is which kind of this thing, and what is that? Isothermal. So gas expands at constant temperature. That's why it has a label of the temperature. It expands at constant temperature. From B to C, of course, when you expand at constant temperature, the gas will take in heat. So it will take in heat. At this point, there is introduction of heat into the system. That means at that point, it's not adiabatic. Heat will come into that system. I hope we are together. But, are we together?
Yes.
Okay, it's a song outside. So I felt like I was saying yes. Sorry, no. So heat is coming inside the system, but at constant temperature. Like we said, this is isothermal. So that's why they the entire heat that is coming in. You should even know if there is constant temperature, that means nothing is happening to internal energy now. So if nothing is happening to internal energy, there is no how you do work. You change volume without heat coming in. Are we together? So for this system to do work at constant temperature, there had to be introduction of heat. Now the next place, which is between B and C. Between B and C, that's adiabatic expansion. At B and C, it expands when no heat is taken in. B and C, it expands when no heat is taken in. So at that instance, when it is expanding when no heat is taken in, from what we have learned, what is happening? How is it able to expand? What is it using to expand? What is it using to expand? What is it using to expand? So that means, that's why from temperature 1, the same temperature of what you had, but for it to do adiabatic expansion here, it now changes from temperature 1 to a new temperature called temperature what? 2. Is that okay with everybody? Are we okay? Listen, first, heat is brought into a system. And when it is brought into such a system, it is at constant temperature. That process is called isothermal expansion. And by the time you have moved from A, B, C, you have been able to do the work. The gas has expanded. But now the idea of CDA is to return the gas back to normal. So that, as we are going to observe in machines, think of a fridge. It will get cold. When you now off it, like, I don't know how to describe it for you to get it. But it's a cycle. What is a cycle? You begin from somewhere, get to a particular point, and then it starts, every other thing you are doing is going backward. So please, C is that point. What did I say this point is called? Isothermal what? Expansion. Constant what? Temperature. For him to expand, what does it now need to come in? Second time, adiabatic expansion. When there's adiabatic expansion, heat is not coming in. So the only source of the expansion will be from what? Internal energy. And who will be affected? Temperature. So if temperature is affected, will it be up or down? Down. I am using it up. So it's coming down. So that's the new temperature. Now from here, please, CD. What does the CD is? Compression, isothermal compression. Now DC. So of course, isothermal compression, when it is at constant temperature, why will it compress at constant temperature? Talk to me. Why would there be compression at constant temperature? Change in U equals to change in U plus W. Change in W. If this guy is compressing, that's negative, right? So that's negative W. Now, if there's constant, this is 0 now. So that means what's happening to your change in U? It's also going to be negative. I don't even understand. So please, if change in U, like we learned, if Q is negative, change in Q rather. If Q is negative, what does that mean? As heat come inside the system, or is heat leaving the system? So please take note that during this process, heat is leaving the system. So here heat was entering, but here heat is doing what? Leaving. Then lastly, D to A is adiabatic compression. And in adiabatic compression, no heat is leaving the system. Adiabatic compression. It's just the exact opposite. Adiabatic isothermal expansion, adiabatic expansion, adiabatic compression. Isothermal expansion, adiabatic expansion, compression, adiabatic compression. All right, so that's that. So that covers that. So you return it back to normal. So what I'm saying is that ABC is aimed at doing the mechanical work, but CDA is aimed at returning it back to what? Normal. Those are the points to know. There's nothing else to know about it. They know who uses this kind of cycle. I said an example is what? Refrigerator. So an assignment for you, please. Look at other systems that can use Carnot cycle. But please, even this particular refrigerator, which kind of Carnot cycle does it use? Reverse. So this is what your refrigerator does. How does a refrigerator work? You know, in this one now, I'm giving him heat. As I give him heat, he expands isothermally. From there, adiabatic, then you are now returning back. But a refrigerator, how does it work? I carry something that was hot to the system. So that's what you carry now. The water you carry into the fridge is hot. Are we together? So when you carry that water to the fridge, being hot, that water now will lose heat. That is coming backward, it's going like this. What you have, listen, what you have without heat coming in or being lost, the temperature will drop. That's when you just carry water inside fridge, the temperature will start dropping. Because of the action of the fridge, the temperature will start dropping. And as it's dropping, you're actually compressing. Compressing, you know, when molecules are coming closer, when molecules come closer, what does that mean? Compression. You know, you change it from, instead of matter, solid, liquid, gas. Liquid, gas is very loose, but solids are very close. So if I carry water now in liquid form, for me to do ice, that means they're coming closer now. That's compression. So this is what you do. Now when you put that water in the fridge, temperature will drop. That's without heat coming in yet, heat loss or gain. At that time, it's adiabatic. When temperature is dropping because of the effect of the fridge, you know the fridge should be cold now if it is on. Are we together at all? Yes. So because the fridge is cold, what will now happen? Temperature is dropping. As it's dropping, it gets here. When it gets here, the next set of compression will now be an isothermal. At constant temperature, but this time around, what is happening? There is heat loss. So when there is heat loss, from what we have learned, there should be compression now. Heat gain is what does expansion. Heat loss does what? So the stuff will compress and it will block. By the time your water has blocked, or whatever I put in the fridge has blocked, or at some point as it's getting blocked, you now start doing expansion. But the expansion is not to the water, it's to the fridge. Don't worry, it's more of a high level stuff to understand how it actually works in machines. So let me leave it. But the truth is that the way your fridge will now work, so that the things in the fridge are cold, but outside the fridge is hot. That's the back of the fridge. Now that metal of the fridge is hot. But it's using the reverse Carnot. Now what of this thing? Auto cycle. What? ACs. Anything you say is correct. Please look it up. You get it. I think ACs use normal Carnot cycle. Like normal Carnot. You just confirm, please. Now for the for auto cycle is similar. What did you for auto cycle is just that's for auto cycle. Please take note that Carnot cycle is the gold standard. Is a gold standard for most machines. So for auto cycle, now let's describe auto cycle. So I'll use the same pattern, A to B. What can you observe from what we have drawn? Now, when you see something, observe another one, there was a show like this now. What does this tell you? There's expansion here, there's still expansion here, right? But when you see one straight file line, what does that tell you? There's no change in volume. So at this instant, it's constant. Okay, so please, let's start. For auto cycle, AB, there is no heat. In auto cycle, it's the same pattern. AB and CD is the same pattern. AB. In auto cycle, it's the same pattern as your Carnot. What happened in Carnot between A and B? Constant temperature, but expansion, right? What was happening? Heat was coming in. In CD, what did we have? Constant temperature, but what? Compression. Stay with me now. AB, it is expanding, but what's happening to temperature? Constant. What's happening to heat? Coming in. In this other one, CD, what was happening to temperature? Constant. But what's happening to the heat? Going out. That's the same thing you have here. You see it's moving this way. Now it's the same pattern. So what makes it different now is the BC and the DA. For BC, the BC is actually going to be a constant volume pressure change. That pressure will change, but then volume is constant. Pressure will change in auto cycle. So between C and B and C, BC, pressure change, but volume is constant. Pressure change, or you can say there are constant volume pressure changes. There is constant volume pressure changes. What do I mean? The volume will not change. Look now, for me to move from here to here, what has happened? There has been what? Pressure. Pressure is y-axis now, P against V. So there is change in pressure moving from here to here. But there is no change in what? Volume. So please. So constant volume pressure changes for both of them. Yes. Yeah, it's isochoric. There will be isochorics. Two of them. Two of them is isochoric. Eh? ATP. A to B is the same thing. Isothermal expansion. C to D isothermal compression. Now lastly, yeah, let's do some more about efficiency. Now how do you calculate efficiency? You know the formula. She had said earlier that efficiency is what? Talk to me now. Who was that person? Work done, Che. Work, okay, output. Output over what? Heat input times 100. I hope we are together. Output over heat input times what? 100. Now, how do we know how much work has been done? How do we know how much work has been done? So there are different formulas to try qualifying this. But I think the one I will use is that for you to get the work that has been, the work output, you check the heat before and the heat after. So Q1 minus Q2 is what we use. Q1 minus Q2. More like this, the person supplying the heat and is gaining. Q1 minus Q2. Can be. There are formulas, but I'll show you that we use. We have one for efficiency. Q1 minus over Q1 times 100. Q1 is input, what you're putting in. Q1 is what you are putting in. Q2 is what remains. So Q1 minus what you have said. Don't even understand. At a particular time, you had a heat into the system. You come back and system, what is left has been lost. The output, what you have used for energy. Now, please look up the formula. Let's do normal. This is LCM. Let's try to do LCM. This will be Q1 over Q1, right? Minus Q2 over Q2. Do we all believe? Do you believe that this is math? Let me clean the board for you to see. Q1 over Q2, sorry, over Q1 minus Q2 over Q1. I believe we believe. Like it is this now that I can collapse and form this. So if I do this, do you believe that Q1 can cancel Q1? So if you cancel, what is my answer? 1 minus Q2 over Q1. All times 100. So this right here is the formula we tend to use a lot. So this is what we do. That this is the heat of the hotter body, Q2. Q1 is the heat of the hotter body, the one supplying the heat. Q2 is the heat of the other body you supply heat to. There was a question that was asked, is not here get more in this your book, sorry. Is anybody with a past question here that has to do with thermodynamics? You must see something about performance, efficiency. Whether you ask us, find the performance of the machine, find the efficiency of the machine, same formula. They will always give you, please, let me give you the idea. So that, I don't know if we will have time. Look up, please. It's one formula like this. Please check for me. Check your notes now. Which formula do you have? You have this one. Cold over hot. Who is on top? Check now. Read from your notes. Yes, efficiency is 1 minus temperature at low over temperature at hot. So it's low over hot. Low over hot. Now let me read this. A Carnot engine, listen, whose lower energy reservoir? Just listen to the question. is 17 degrees Celsius. Remember, I told you the temperature, you have to change it to what? Temperature, you have to change it to what? Kelvin. Has an efficiency of 40%. By how much should the temperature of the higher temperature? Oh. Let me start with something that is godly. A system operates between two temperatures, reserving 450 Kelvin and 900 Kelvin. This one can come out in your exams. A system operates between two temperatures, reserving 450 and 900. Which of those energy reserve? 900. So they say calculate the performance of the machine. Performance is simple. It's just for you to write out what is the formula for performance. 1 minus temperature of coal over temperature of hot reservoir. Please just write it in your notes. Efficiency slash performance. Temperature reserving 450 K and 900 Kelvin. Are we together? 450 and 900, are we together? Calculate performance. How do we calculate? What's your answer? Sermon of God, I trust you. What's your answer? 50. That's 1 minus 450 over 900.